name is Ella Marshall. I am a biomedical engineer and also the team lead for Team 25055.
My name is Dennis Shaw. I am the optical engineer for Team 2555 for Luma Vici Medical.
My name is Kyle McAleese. I am the mechanical lead on Team 2555.
Hi, everyone. My name is Gabby Andriakis, and I'm the team's biomedical lead. I'm majoring in biomedical engineering.
My name is Omar Corona Ramos. I am the electrical lead of the group. I am majoring in electrical and computer engineering.
Hi, my name is Sarah Bixabarbayev. I'm the hardware integration lead of this project.
The students get along really well. That's one of the most important things. To get along, to trust each other, so that you're not afraid to throw out crazy ideas. And when you have that kind of environment, then I think really good ideas are generated.
Approximately 15 to 25% of hospitalized patients receive urinary catheters, putting them at risk for UTIs, urinary tract infections. Urinary tract infections occur when bacteria enter the urinary tract and infect any corresponding structure such as the bladder or the urethra. Catheter-associated urinary tract infections are one of the most common hospital-acquired infections, accounting for up to 40% of the infections.
What I thought to myself was, I trained in surgery here at the University of Arizona almost 30 years ago, and it didn't seem that we had come that far from how we treated infections at that time, and it seemed like maybe there would be a better way. We had already been studying the use of ultraviolet light in my own office for treating tissue, for maintaining a sterile environment for treating tissue. And it occurred to us that we could possibly use antimicrobial light in another fashion to help treat infections in the hospital.
Catheter-associated urinary tract infections increase morbidity, mortality, healthcare costs, and patient costs in hospitals, making them a tax on both the patient and the hospital. To prevent urinary tract infections, the CDC recommends changing catheters using aseptic techniques and washing your hands in between, but there still leaves a lot of room for infections to occur at both the port complex between the catheter and the bladder bag and at the drainage port of the bladder bag, in addition to the natural risk of infection just at the urethra. Our project, the Self-Disinfecting Urinary Catheter using safe antimicrobial light, helps to overcome this by leveraging a novel disinfecting system that does not require pharmaceutical options and instead uses an antimicrobial wavelength of light.
The overall requirements of this project were to achieve 99% bacterial reduction while using 405 nanometer light to reduce catheter-associated infections and also ensuring the safety of the patient.
Initially, all of our proposed solutions were very unique ways of propagating light down a catheter. We knew that our catheter needed three main components: a light source, some sort of optical fiber, whether that be internal or external, and then some sort of modification to the fiber to have radiant diffusion of the 405 light onto the patient. Initially, we chose a completely diffuse fiber for this, but supply chain issues and issues acquiring the fiber at all popped up very quickly, and it became very apparent that we needed to take a traditional optical fiber and a traditional optical fiber coupled light source and then modify it further to get what we needed. The final design of our fiber run catheter was consisting of four main components, the first of which is a 3-port Foley catheter. We chose this because it had an additional port on the side where we could completely run any optical system we wanted through that port, and it would stay dry and out of the elements and out of any potential biological contact. The second was a high-powered 405 source. This would provide us plenty of light to run down our catheter. And then the next two components were the fiber line itself, which is a 400 micron optical fiber. And then the fourth component is the end of that optical fiber. We have a diffuse coating that we applied to the end of it, which would increase our diffusion radially. All four of these combined made for a catheter that could reliably and accurately deliver a dosage of 405 nanometers to kill microbes, but be within the limits of human safety.
Later on to the project, we proposed a different system for disinfection. This would run in tandem with the initial system. This was a LED clip device that's clipped on the catheter collection bag tubing above the collection bag in order to prevent ascending microbes from causing a UTI. The LED clip is simply clipped onto the catheter tubing, and a simple on-off switch begins disinfection.
The question we had was, how do you experimentally verify that the efficacy of a disinfection method, especially one that will be implemented in an environment with numerous unpredictable external factors? We started with a thorough literature review, learning about the efficacy of 405 nanometer light and understanding its current applications. From there, we created our own experimental setup to assess the functionality of our system based on another setup found in the literature review. So this project involves novel disinfection methods that have been researched. So the effectiveness of our system is not well documented, but we partnered with Dr. Kelly Bright and the West Center Pathology Lab, which allowed us to use their lab space for biomedical research. Using a control and a test setup, we pumped pasteurized urine through a simulated bladder and catheter system with E. coli inoculated at multiple locations to model likely conditions in which a catheter might become infected. We collected hundreds of assay plates and reviewed our results.
It's super exciting to be involved on a project using this novel form of disinfection and something so simple as a wavelength of light. Thank you for watching this video. We will see you at Design Day.